Okay, so we got a lot of enhancements. 3-axis milling, obviously, because 3-axis is the most used toolpath methods that we have. And initially, what we've got here is we've added toolpath optimization. Toolpath optimization tab up here, and if you look down, you have feed rate reduction factors, feed rate reduction parameters. Now, these feed rate optimization parameters, we did have them in the product, but it was only after the fact. In other words, you had to go into the toolpath editor and apply feed rate optimization to a toolpath after you have generated it. And then if you generate it again, then you would have to go back and add them again. So we've modified this and moved the feed rate optimization up into each of the toolpath operation dialogues that supports it. So basically all 2-axis, if you have any linear toolpaths in 2-axis, you can apply feed rate optimization. Also in 3-axis, all of the linear 3-axis, any of the 3-axis that cuts in levels, you have basically, if you look on the left here, we got one level here. This is facing, obviously, but any 3-axis that also is similar, where you're cutting in levels and you have a toolpath on a flat plane that's wrapping around corners, you can apply the toolpath optimization parameters. So if you look at these dialogues, let's take a moment to look at these pictures we've got here. So on the left, we've got the toolpath optimization, feed rate reduction parameters. Okay, so currently, if you look at these two parameters right here, where you see, let's see. Hold on a second. Okay, look at my feed rate.
The most important parameter is the corner angle.
Yeah.
So depending on your corners, so the idea here is when you hit a corner, if your machine wants to slow down the feed rate, then this is where you will set the corner angle. So if you have a 90-degree angle, anything steeper than 90 degrees in those corners, if you want to actually slow down the feed rate, you'll specify that angle, corner angle here is set to 90 in this dialog. And then, of course, the distance where you want to start the feed rate reduction. Where do you want it to start? So if it's a linear motion coming into the corner, we break up that linear motion based on that distance you specify, and then apply that feed rate. So again, after the corner has been cut, when do you want to reset the feed rate back to the normal feed rate? That's the next parameter. So yeah, these are the controls we have. And then obviously the feed rate reduction percentage. How much do you want to reduce the feed rate as you're going into the corner, and then ignoring certain types of motions also. So quite a bit of control. And we see this as an area that we're going to be constantly working on to improve feed rates and other sorts of optimizations for the toolpath in the coming releases.
Okay, thanks, Joe. What I was getting at is the feed rate reduction percentage. You see this is set at 0.25. So if you look at the G code here on the right, we see with no feed rate optimization. So the cut feed rate was set to 10 in the actual the cut parameters tab, or in the feeds and speeds tab, excuse me. And then the G code in the middle is with the feed rate optimization applied. You see you have your initial feed rate of 10, and then when it approaches each corner, it drops down to 2.5 or 25%. So that'll do that through the entire toolpath and make those adjustments. And I did want to mention also, one of the main reasons to use this is to alleviate some of the stress on your CNC machine. If you're noticing a lot of jerking motions, especially at corners, yeah, that's because the CNC machine is wanting to apply the full cut feed rate for the entire path. and obviously it has to stop at a corner before it changes direction. So that's the jerking motion you're seeing. So that's the main reason why you want to apply some feed rate optimization. It'll slow down right before it gets to the corner. It'll stop, it'll speed up after it turns the corner, and you won't see that jerking motion in your CNC machine. The mechanisms, the servos will last a lot longer. Obviously, it won't wear out as quickly. So that's another thing to take into account for feed rate optimization. Okay, this is one that a lot of users have run into, and what we're doing here is we're applying meshing parameters ahead of time, and then when we calculate some of the 3-axis operation types, it takes those meshing parameters into account. Joe, do you want to take over this and discuss what's going on the left here as to
Okay, yeah, sure. What happens in our 3-axis toolpath methods is when we have a surface, when you're machining surface, we actually start out with the mesh. We create a mesh, and then once we generate the toolpath, then we do some internal math to refine the toolpaths to the actual surface. If the starting mesh is not very good, then sometimes we run into these kinds of issues you see on the left. And these typically, don't happen all the time. So it's a very small percentage of cases this happens, but it can be pretty annoying if you suddenly in the middle of your large part that has hundreds of surfaces, you have one surface that's given you, behavior like this. So this has been annoying to some of our customers where you're doing some sophisticated work. So what we have done to improve that is to give more control to the users to actually set the initial meshing parameters to get the toolpath computation started. And so one of the things that the users can control now is the aspect ratio of the triangles in the mesh. Aspect ratio is basically the length divided by the width. So if you have an aspect ratio of 0, it's going to use the default mesh. Whatever the default meshing that was being previously used is going to be used. But if you said the aspect ratio is 1, then the mesh triangles are going to be very regular. So the width is going to be the same as the height of the triangles in the mesh. So you're going to get a very regular mesh on the surface. And then you can also control the minimum edge length to control the number of triangles you're getting or facets you're getting in the mesh. So when we we've done some heuristic testing on it, and then we have some data on what are the right things to set up, and we can share that with the customers. We've noticed, and the edge length is obviously dependent on the part size. With the aspect ratio, typically if you wanted regular triangles, you want to set it at 1. And when you do that, the toolpaths are quite a bit improved. But one thing to notice and one thing to be aware of is, you can take the performance hit here. If you set up your mesh parameters to be too tight, it'll create meshes that are quite dense, and you might get a great toolpath, but it might be just overkill for your application. So a word of warning there. So you got to be a little bit. You got to do a little bit of experimentation to see that. But what Don's going to be showing is the types of surfaces that this improves. This machine control actually improves the toolpath quality on.
Okay, thanks.
All right, Don, go ahead.
Okay, and on the right, you see the result. So basically, you got these jagged motions in here. I'm going to show you this part and see why it does, not necessarily why, but I'm going to show you in effect when it happens, and then we can regenerate that after you set the meshing parameters and get a really good toolpath. This is something that users have run into recently, and this is our method to make it a lot better. Okay, so let's go.
Actually, the problem, sorry, Don,
the
problem occurs only in one class of surfaces, which is rule surfaces. When you have rule surface where the one side of the rule surface is quite a bit different than the other side, particularly in this case that Don is showing. It's a twisted rule surface where the rulings are quite a bit different from one side to the other, and that's when you see these issues, and that's where these machine parameters will be applied.
Mm-hmm. Mm-hmm. And again, we're going to show you that in the actual part coming up in a demo. Okay, here's an interesting one. In 3-axis, we provided the ability to use both surfaces and curved regions. And when you do that, you can, similar to the way, in 2-axis operations where you have a nesting perimeter, like you have an outer perimeter and an inner perimeter, and then the toolpath is actually between the two. And if you look at the picture over here, we're selecting one part surface in the part surfaces tab, and this is parallel finishing, 3-axis. And then over on the containment regions tab, we've added these curves, as you can see in orange here, that go around the base of this feature. So the result then is parallel finishing will only take place between those two areas to the perimeter of the surface, and then stops at the inner curve region. So this is something that if you have some complex features in 3-axis that you need to cut, this will come into play and help you out. A little bit more control in the 3-axis parallel finishing. And it's not, correct me if I'm wrong, Joe, I don't think it's just in the parallel finishing. Is that the case? It might be another. Well.
It's in all 3-axis. It's on all 3-axis methods.
Okay, good. So, and again, I wanted to mention, if you guys got any questions, please add them into the questions tab in your dialogue, and we'll be looking at them in the background and we'll get them answered for you. Okay, so what we have here is 3-axis milling enhancements. So it's 3-axis drive curves and surfaces combination of geometry. So previously, in previous versions, you either did surfaces or you did curves. Okay, so if you was doing curves and you wanted to get the same outcome, you would have to select all of the curves around the edge of the surface, then all the curves around here, and it would figure that out and cut between them. So now it just makes it a lot easier if you're going to avoid features like this in 3-axis. Okay, here's a good one too in 3-axis. We've added corner cleanup loops. If you're unfamiliar with corner cleanup, so let's just look at the pictures here. Yeah, corner cleanup is actually in 2-axis, and now we're adding it in some 3-axis operation types. So I believe it's also already available in the cutting in levels in 3-axis, such as clearing flats on horizontal roughing, etc. But now we've actually added it to a toolpath that is not planar. This is one of our advanced 3-axis methods, 3-axis projection pocketing, where the toolpath is calculated and then projected in the z-axis down onto the part. So in previous versions, if you look on the left here, the result would be these sharp corners. Okay, so it would calculate the offset. Okay, and then it would project it down onto the part surface, and then you'd have these really sharp corners that could cause you, again, some jerking motion in the CNC machine. As the tool goes to those corners, it has to stop, change direction, etc. So
and more importantly, there might be, if the corner is really steep, you could actually end up leaving material there because the tool is turning, very dramatically there, and so these cleanup loops actually will go in and clean those material stubs that are sitting on the part.
Yeah, as you can see up here in the corner cleanup loop, you see that the loop, I have it set to outside. Okay, so the loop is extended to the outside perimeter of the corner which Joe mentioned that adds some cleanup right here in this pass, right there at the corner itself. But it also allows the tool, to turn that corner without so much jerking motion on the machine, on the CNC machine. So that is 3-axis milling, and that is corner cleanup loops and 3-axis projection pocketing. If you don't see 3-axis projection pocketing in your 3-axis menu, this is a pro configuration operation type. So if you don't see that, that's the reason why you may be running expert or standard. If you need these types of machining methods that we're showing right specifically here, just let us know when we'll send you information about upgrading to Pro. So again, just before I move on, corner cleanup loops and 3-axis projection pocketing. This is before on the left, this is after in the center, and then on the right we see the control in the cut parameters tab of the 3-axis projection pocketing dialog. Okay, so let's talk about our 3-axis enhancements for version 2025. The one I'm going to show you here is we now have feed rate optimization available in all leveling toolpaths. By leveling, I mean not just 2-axis facing, pocketing, profiling, etc., but also in horizontal roughing, where you have flat level cut levels, and any other operation type that creates a flat planar area. Okay, so in this particular part, we have a couple of parts and they sit on top of a plane, okay, that we're going to use to machine them. So let's look at what we have here. We have horizontal roughing. Let's take a look at that. Okay, we got no control geometry selected, so it's just calculating what it can remove. We got a flat mill, 1/4-inch flat mill, cutter parameters. These are all straightforward. You'll be familiar with all of these. Let's go ahead and look at the cut levels. So here, pretty much standard. We have an extra button here called Add Stock. I'm going to go over that in another part in just a moment. And then also engage or retract. We're using a helical engagement. We're doing some arc fitting. Toolpath optimization. So here, if you're familiar with our feed rate optimization in version 2024 and prior, you may know that feed rate optimization was an edit that we did after the fact. So you could only do it in a toolpath. Let's save this, I'll show you. You could only do it in the toolpath editor, okay? And if we go to the global edits, okay, and you'll see that we have a number of commands up here, and one of them is feed rate optimization. You'll see that all of the same parameters now are in this tab called toolpath optimization, the section called feed rate reduction parameters. So these are the same parameters. The difference is, the major difference, however, is that prior to 2025, feed rate optimization was an optimization that you applied to an existing toolpath that was already generated. Okay, so you go through your CAM phase, you have all of your operations generated the way you want them, and then you would go in after the fact, edit each toolpath to apply feed rate optimization, which obviously you probably figured out what the downside of that is, that if you make a change to the toolpath and regenerate it, the feed rate optimization parameters are lost. So you got to reapply them again. So the enhancement in 2025 is that we moved the feed rate optimization or the feed rate reduction parameters into the toolpath dialog so that they are applied when the toolpath is generated. So there's no other side steps that you have to do to get toolpath optimization implemented. So let's see what we've got for toolpath optimization for the horizontal roughing. The main thing to look at is the feed rate reduction percentage. So we want to reduce the feed rate 50% or 0.5 when it reaches a corner of less than or equal to 90 degrees. So anytime it comes to a corner that's less than or equal to 90 degrees, the feed rate's going to drop by 50%. Okay, and then it's going to pick up at 100%. And these are the distances. Say an eighth of an inch before a corner, it's going to drop 50%. An eighth of an inch after the corner, it's going to go back to 100%. Okay, so let's go ahead and regenerate this. Okay, and let's go ahead and look at what the feed rates are. So we have a cut feed rate of 4 inches per minute. Now, in version 2024, that would be the cut feed rate throughout the whole path. It would not change. Come to a corner, your router will have to come to a complete stop and then start and stop, start and stop, and you actually can see that jerking motion on your router if you have a lot of sharp angles in your toolpath. Now we have other things you can do, such as some looping and stuff like that, which helps also. But now you can actually control the feed rates at those corners. So toolpath optimization, it's enabled. Okay, and the feed rate is set to 4 inches per minute. Okay, so let's generate that. Okay, let's see what our post is set to. Our post is set to Haas CAM. I think that which should be all right. Let's go ahead and pick OK there, and let's post this and see what we got. Okay, so let's look at this. So our feed rate optimization was enabled. The feed rate was 4 inches per minute. Okay, so at the corners, we have a lot of corners. So at the corners, it should drop by 50%. So what you're seeing here is we got a feed rate of 4. It's dropping to 2, 50%. All the way through here, it's dropping 50% at corners. Anytime where you see an F2 is where it's dropped from an F4 to an F2. So this is feed rate optimization in action, and how it looks in your G code itself. If you don't see the reduced feed rate in your posted G code, you need to make sure that you have it enabled in the operation dialog, which is called toolpath optimization. Make sure that is enabled, and make sure you have the parameters set the way you want them to be set. Okay, let's cancel out of that. Let's see what else we have up here. So that was horizontal roughing. It also will not apply to horizontal finishing that's not planar. So we have a contoured parallel finishing. It will not apply to that situation. But if we go on down to the facing, this is a planar toolpath with a lot of sharp corners that will apply there. So let's take a look at the facing. So we have use optimizations is enabled, and we have the feed rate reduction percentage set to 25%. Let's take a look at what we have for feed rate. So we have the cut feed rate at 10. So in the corners, it should drop to 2.5. So this is 10 inches per minute. At the corners, it should drop to 2.5 inches per minute. Let's take a look at it. Should be 1/8 prior and 1/8 of an inch after each corner. Okay, so let's generate that again. Let's post that. So here you'll see that we have a feed rate of 10. Okay, and at every corner it's dropping to 2.5. So all throughout the whole part, you'll see it drop to 2.5 at each corner. At the beginning, it'll drop, and then after it turns the corner, it will speed up to 100%. So that's feed rate optimization in action in 2-axis facing. Let's go ahead and minimize that. Let's take a look at the profiling. Okay, so your feed rate optimization is not going to, well, we do have it in there. You can apply it to profiling as well. Okay, so that is 3-axis feed rate optimization. Let's take a look at our next 3-axis part, which is, let's take a look at this one here, which is faceting controls. Now, you may have noticed, and this is only in certain surface cases, such as ruled surfaces. Let's turn our surfaces on. We got 2 examples here. Let's turn that off. Okay, so the problem the problem applies is when you have not two, but a ruled surface. A ruled surface is one that is a direct connection between one curve and another curve. So it's like a ruler. It's like you put a ruler on each of those curves and you just run in the ruler down, as it stays on both curves and, all the way to the end. So as you can see that it's any cross section in this surface is a straight line, but it's a twisted ruled surface, which is a very complex surface. And in some cases, the actual internal generation of the coordinates and the facet points on that surface can get skewed. Okay, and this is a problem that we've been working on and fixed in version 2025, and a lot of users out there, if you're one of them, you'll be very glad to see this. So how do you implement this? If you go to the CAM Preferences dialog, go to the Machining tab, you'll see Meshing Parameters. Okay, so what it's doing is it's using these parameters here internally to calculate the each control point on the surface that we're going to use to actually generate the tool path. So we have our part is in millimeters. So we have an aspect ratio, which is the relation between the length and the width of each facet in a mesh. If you're familiar with mesh geometry, you know that a mesh is a collection of planar triangles, okay, that define the entire object. Okay, so we're setting the aspect ratio to 1.41. That's the relationship. Length divided by width is the ratio. And then we're also setting the maximum edge length. In this case, we're setting it to 1 millimeter. So let's go pick OK there. So if we look at the parallel finishing, before we set the meshing parameters, you'll see that there's a lot of jagged lines in that tool path as that tool rides over that ruled surface. This is bad. So you're not going to want to cut it like that. So what we've done is we've implemented the meshing parameters that once you set those and you just go back in and regenerate the operation, you'll see that it's cleaned up for you. Nothing else you need to do. You don't need to create a mesh in Rhino or in Visual CAD. You don't need to create a mesh to try to fix those errors in the toolpath. That's all fixed in version 2025. And we have another example. So here is a ruled surface. Okay, it's not as extreme in the other one, but it is relatively complex. We don't have a straight line here. We have a curve on this end with a straight line on this end, which causes the ruled surface to twist around. So let's take a look and see if we can see the problem. So here's our toolpath. And in order to see this, sometimes you need to have a really dense step over in order to see the phenomenon we're looking at. So you can start to see it. Let's go into the Simulate tab. Okay, so the part is turned off. So what you're seeing here, you're seeing those facets. Let's see, that's a good way to get it right there. You see those rectangular areas in the part or in the toolpath itself. Okay, so that will be seen when you machine this on the router. Okay, so now if you set the meshing parameters here, again, you set it over here, machining, meshing parameters, and we generate the toolpath, we added a second toolpath, you'll see that those faceting phenomenon are gone. So you will not see those in the machine surface, okay? Very, very sought after fix, enhancement, whatever you want to call it. This should not happen now in version 2025. Okay, let's keep going to some additional 3-axis enhancements. Let's go and look at, get my cursor back here. We'll go ahead and we're going to look at this one here. Okay. Now in 3-axis operations, you can combine, for your control geometry, you can combine both surfaces and curves, okay? And they act in a nesting type relationship. So in this particular example, we have a surface, okay? This is our base surface, okay? And then we have a feature on top of that surface that begins, it rolls up, off of that surface, okay? Now, to cut this, you may not want to cut this feature as part of the surface. You may want to just do the surface first, okay? So in cases like this, you can now select both the surfaces and the curves in order to get a nested effect. So let's look at the parallel finishing operation. So in this particular example, we have a part surface selected on the surfaces, part surfaces tab, okay? So this is the green edges here, that's our surface, our base surface. And then for containment regions, we're selecting these perimeter curves, okay? All the way around the base of this feature. So what happens now when you generate that, the inner curves will serve as a void region. So the tool will not violate these inner curves. So I know you may be wondering, well, these curves are completely inside the surface. What happens if they don't? What happens if they fall off of the surface? Okay, so we'll get another example here. If you look at the top view, okay, look at the top view, and let's go into a wireframe for now. So we got the surface and we got a planar rectangle here, okay, that is partly on and partly off the surface. Let's take a look at how that looks like here. Let's turn the surfaces back on. Okay, let's go to, well, let's just take a look at it. As you can see, it just, creates an avoid region where that, where the curve geometry intersects with the surface geometry. It treats that as an avoid region. Okay, so think of it as having an avoid regions in 3-axis, where prior versions avoid regions basically applied the 2-axis, but you could do it in 3-axis, okay, if you selected the curves in a certain way, like edge curves of the surface and edge curves in here. It will figure out that some of these curves are inside the other curves, but it's more of a complex situation. You could run into possibly some conditions where it could be a problem, okay? So now you can use both surfaces and curves together to generate your toolpath in 3-axis methods. And a lot of these 3-axis methods you will see that you can put both containment regions and part surfaces in the same operation. Okay. Okay, let's look up one part that I wanted to show you. I'm going to show you a couple of things on this part. Where is that? Right here. One of the things, an enhancement that we made to our professional configuration in relation to corner loops in 3-axis projection pocketing. Now, 3-axis projection pocketing, you'll see on the 3-axis advanced menu is projection pocketing. Okay, in projection pocketing, what happens is the toolpath is calculated on a plane. This is internally. It's calculated on a plane, and then those toolpaths internally are projected down in the z-axis onto the part. Okay, so the resulting toolpaths are three-dimensional. They're not planar toolpaths. They're on the part surface. Okay, so that's just a quick definition of projection pocketing. So let's take a look at what we got here. Prior to 2025, in projection pocketing, let's take a look at that. We have a surface selected. We have our ball mill tool. Okay, and prior to that, you didn't have the cleanup loops. So this is what's new right here. You have corner cleanup loops, none inside and outside. So prior to 2025, there wasn't any, so I have it set to none. So what you get is these very sharp angles from one direction to another. Just as it can be a problem in planar, 2-axis planar toolpaths where the router has to stop and start at each corner. It has to do that also on 3-axis parts. So what we've done here, instead of implementing feed rate optimization, which I think there is in it, let's take a look. No. So there is no 3-axis feed rate optimization. But what we've added is the ability to add loops at these corners. Let's take a look at what that looks like. So on this one we have it set to, okay, corner cleanup loops outside. So this is the effect that you get. It's in effect what it's creating is a high-speed toolpath in 3-axis, okay, where the tool, instead of just stopping and starting, it can continue past, do this loop, go around. So each one of these angles here are less than 90 degrees, so it's a lot easier on your router, okay, and also on the cutting tools, and you get a better surface finish, because what you'll notice is if you don't have these loops, you'll have some material that may be cusping and left on the part in these particular areas where you'd have to go in either manually clean that up with a emery board or sandpaper if it's wood in this case, but with the loops it helps get rid of that excess material, have a better surface finish, less wear on your tool, very less wear on your CNC router. So that's 3-axis projection pocketing in the professional configuration. If you want to look at these operations, you can run the product in demo mode in the professional configuration. We have a video for that on our website. Just go to MecSoft Corporation on YouTube and search for that, and you'll find that video. Okay, so what do we got next? Okay, there was one other thing I wanted to show you while we had this part displayed. So you've got your part set up. Okay, let's go back over here. Let's turn the world coordinate system. So we got a world coordinate system, and we have a work 0 up here, which appears to be at the corner of the stock. Okay, yes. So we got our work 0, we got our stock, everything looks good. Okay, so you run this on the machine, and then you get an error on your controller. It says machine limits exceeded in X or Y. In this case, it's X. Okay, so then you're scratching your head and you went, okay, so where do I figure out how do I move my part to make sure it's inside that my machine limits? Okay, and we actually get a lot of support emails on this. So what we've done in 2025 is we've given you the ability to see your machining envelope on the screen. So if you go up to the machine definition dialog and you set your min-max translational limits of your router, and these are values that you will find in your router manual. If you can't find it, just contact your router manufacturer and they'll supply those values for you. Just enter those values here. Check this box. This is new. Display translational limits, and you'll see that the limits display on the screen, similar to a stock model. But let's look at what's going on here. We see that the part is too far outside the machine limits. So every toolpath on this part that exceeds past this translational limits in our plugin will flag as an error and alert you when you simulate that toolpath. If any part of a toolpath simulates and goes outside of this limit, then it will flag you and let you know before you get to the router and before your controller throws the error and you've got a part half machined and you're wondering what's going on. Okay, so this is a good thing to look at every single part. Make sure your translational limits of the machine is set in the machine tool setup dialog, and check this box and you can visually see your translational limits as it relates to your part in your setup. A very, very useful enhancement, okay, for 2025. Okay, let's move on. Our next enhancement in 3-axis is in adaptive roughing. Let's go ahead and look at that. Here we go. So we have a part here that we want to rough out these inner chambers using 3-axis adaptive roughing. Okay, now adaptive roughing is located here on the advanced 3-axis menu. If you do not see adaptive roughing on your menu, it means that you have not purchased adaptive roughing. Adaptive roughing is a as we mentioned here in the video, a module, sort of like a mini module. It's a technology that you can add to any existing configuration to use adaptive roughing. And adaptive roughing in and of itself is a method that during the computation and the calculation of the toolpath, it does a lot of adjustments based on your geometry and your tool and your toolpath parameters to get a very optimized high-speed toolpath. Now, what have we done? We've had adaptive roughing already in prior versions, but what we've done in this particular 2025 version, even we made a few tweaks and enhancements to it that I want to go ahead and show you. So let's look at the adaptive roughing dialog. We're using a 1/2-inch flat end mill. The cut parameters, everything looks pretty straightforward there. What we've done is in the engage and retract area where you assign the values for your helical entry. And in adaptive roughing, everything is about not slowing your tool down. We don't want to make your tool stop and change directions. We don't want it to stop at all. So in most cases, at each cut level, you'll see one helical entry and one exit. You may see areas where the tool may have to rise and transfer, to get down to another area. You may see that, but even in those areas, we add arc motions to facilitate the high-speed cut pattern. So if you look at the entry, engage, retract, and material parameters, there's our helical motion, and also you can apply toolpath optimization if you want. But this is a method that cuts in levels. It's a roughing method. So let's take a look at the view the toolpath in levels display. So we got each one of these levels. Let's look at the first level here. As you can see, we have our helical entry, one helical entry at each level, but you'll also notice that we have a retract and a transfer to pick up some more material over here. So you'll notice here that in the retract, we have an arc motion and an arc motion and a retract motion, okay? So these arc motions facilitate the high-speed cut pattern itself at higher feed rates, okay? And then we also have arcs on the re-entry over here. So the enhancement is that we now enforce the helical entry at each cut level regardless of the depth of the cut level. In prior versions, the depth of the cut level may not have allowed us to put a full helical motion, or for whatever reasons, it may have skipped the helical entry and just plunged down to the entry point. You'll see now that we do not do that. We force a helical entry at every cut level, and we also add arc motions if you need to retract and move the tool to another location. So that's primarily the enhancement we did in 3-axis adaptive roughing. Okay. Okay, we got one more enhancement that I want to show you in 3-axis. Let's go over here. Let's turn the toolpath off. Okay, so you may have seen this part before. We've used it for a number of different things. But with the enhancement that we did in 2025, you'll notice that this part has flat areas. Okay, so we got a flat here, 4 flats up there, we got a flat in the center, we got a flat right here, we've got a flat floor inside. So if you're familiar with horizontal roughing, you know that you can clear flat areas automatically with the toolpath. So let's go ahead and look at the horizontal roughing. Okay, look at the cut levels tab. So what we've added is this checkbox to add stock. Okay, and by adding stock, what that means is users, a lot of you have asked for the ability, I don't want to clear the flat. Okay, I don't want to cut all the way down to the flat because I have a stock set to 25 thousandths. Okay, I want that stock to apply to the clear flat area. I don't want it to cut all the way down. I want to clear those flats myself with a separate operation. I have better control of it with a newer tool, say, to get an exact better either surface finish or an exact a better positioning of the flat, etc., etc., etc. Okay, so now what you can do is you can add the stock back to the flat area. So let's take a look at what this looks like. Let's go to the multi-view port. So we have clear flats enabled. We have clear flats enabled. We don't have stock enabled. So this is what it was like in 2024 and prior. And what you got was an additional toolpath at each flat area. Okay, so you have one there, you've got one down here, you've got one here. So it just interjects a flat area where it needs to. Okay, but the rest of these cuts are roughing operations. So you're leaving 25 thousandths on the part everywhere else, but we're forcing you to clear this flat area in a finishing operation. You may not want to do that, and a lot of users don't want to do that. So what we've done is we've added this checkbox, add stock to your flat area. I want to clear it, but I want to clear it at a stock value above the part. So let's take a look at what that looks like. So now what you'll see is we don't put that flat additional planar motion on the part. We move up by the stock value, in this case 25 thousandths. So you'll see that there's 25 thousandths left on your part that you can come in and you can clear off the way you want to clear it off. And again, here it is here, up 25 thousandths. And if we look at a wireframe, you'll see that inside, I believe that bottom floor is right here as well. We backed off 25 thousandths. So to reiterate, in 3-axis horizontal roughing, cut levels tab, clear flats. You also have this option now of adding stock. So if you don't want to clear your flats, but you want to cut the flats, but you want to leave the stock amount, just check that box, regenerate your toolpath, and you'll be all set to go.